Good afternoon, everybody. It's now 2:06. So let's get started with the do now. This should be a review of Chapter 7 from last week. So you have to classify the reaction, balance the equation, and then write it out in words. You may not have had time to do all that if you're just joining us, but make sure this is something that you can do. For those of you who had time, how would you classify this reaction? What type of reaction is it? I absolutely agree. This is a double replacement. We're forming some kind of a precipitate as a product. And we've got our ions kind of swapping places here. So the potassium, it starts off with the sulfate, ends up with the hydroxide. And the barium does the opposite. Now, I'm not going to ask you to put in your answers yet for balancing the equation. I'm going to kind of show how that works as a refresher, and then you can let me know how you did. We always start by looking at each of the elements or ions just kind of take a lay of the land. And we can keep those ions together because they appear on both sides. So we fill in how many of each thing we have on the reactant side, which is the left side. The product side is always the right side. So we've got a couple of places where we're not balanced. We'll start with the potassium. To balance it, we're going to add a 2 in front of the compound on the product side that has potassium. Then we're going to take stock of what we did, because we made some changes to more than just the potassium. I like to make this chart every time because it helps to make sure that you're catching everything. So if you change one thing, you want to make sure that you're not making any mistakes along the way. If you feel comfortable to just do an initial chart and a final chart, that's totally fine too. We didn't do anything to the reactant side, but we did multiply by 2 for our potassium. And that means that we also have 2 hydroxides. The barium sulfate stays the same. Now we're balanced. So if I were to ask you to write the coefficient from the balanced equation for, say, barium sulfate, you would say 1. Or if I asked you the coefficient for potassium hydroxide in the balanced equation, you would say 2. So how many of us were able to get that, or at least feel confident that they could get that, given enough time? You can raise your hand or just say me. Okay. So make sure you can balance those equations because we're going to build on that. Yeah, that's fine. You can still do some more practice. For chapter 7, there's some chapter 7 practice already, should already be posted. Now for this last one, I'm not going to ask you to write it in the chat, but I'll write out what I have. As long as you have something similar to this, then you're fine. First thing you always want to do is write out what your reactants are and the physical state each compound is in. So I combined it and said aqueous solutions of, and then put potassium sulfate and barium hydroxide. So instead of saying aqueous blah 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 and aqueous blah blah blah, you can just say aqueous solutions of. That's just a grammar thing. It's just a preference thing. Now we need to write about the arrow. And all we're doing is mixing two solutions together. So you can say aqueous solutions of potassium sulfate and barium hydroxide are mixed to yield or produce or give, whatever verb you like. Then you go on and talk about your products. We've got solid barium sulfate. That's our precipitate. And aqueous potassium hydroxide. Sure, I'll repeat the whole thing. So the first part, we have our reactants, aqueous solutions of potassium sulfate and barium hydroxide. With the yield arrow, we don't see anything special. So we're just going to say that they're mixed to yield. Then we've got this solid barium sulfate. That's a precipitate. We said that this is a double replacement reaction. So we are bound to see some kind of a solid form along with a new aqueous solution. And the other product is aqueous potassium hydroxide. So this goes over the majority of chapter 7. No problem. This goes over the majority of chapter 7. There's still the single replacement reactions where we talked about the activity series, and we also talked about the solubility rules. So we didn't cover that here. But again, there should be a chapter 7 additional problems in the chapter 7 folder where you can do some more work on those. Any questions before we move on? So this week we're covering chapter 8, and we're actually splitting it up into 2 weeks. You'll notice that there is not a chapter 8 video posted yet on YouTube. There will be, I promise. Sometimes I have a hectic weekend too. But we're going to spend 2 weeks on this. So your mastering chemistry homework is not going to be due this Sunday. It's going to be due the next Sunday. We'll talk about that. You will have a chapter check-in that's going to be short, just a couple of questions to make sure that you understand what we did so far. But your mastering chemistry won't be due until after we finish. Yes, question. Your next test is going to be after we complete chapter 8. And I don't remember if I have that date in the reminders. Yes, it should be the week after we finish chapter 8. It's in the syllabus, so you can definitely check there. I just don't remember offhand what the exact date is. Thank you. 28th through the 30th. I did not put up a video for chapter 8 yet, but there will be one this week. So my apologies for that. You will see one this week. So we're going to go through part of chapter 8. The video will cover the entirety of chapter 8. And we'll finish up what we don't get to next week. But I figured most people are not going to touch that video anyway because of the exam, especially with the mental health day. So everything got messed up. But that's okay. The other bit of information I want to give you on both ends is midterm grades. So those are due for instructors on Friday. I'm going to try to get mine in on Thursday. So what's going to be included is everything that we did up through this last exam that y'all took over the weekend. So that also includes your Chapter 7 Mastering Chemistry assignments. There's no extra midterm test or anything like that. But your grade that is reflected by your midterm grade will have everything up through exam 3, 2. I'm like, where are we? Exam 3. Yes, I have multiple classes and there's different numbers of exams. So I'm always like, where am I today? Tuesday is a long day. So my apologies, y'all. So it's going to take everything into account up through exam 3. Just giving you all the heads up. I'm going to put those in about Thursday. So if you have makeup work to do or something like that because you were sick or what have you, try to get it in, even if it's ahead of the deadline that we've established, because your grade is not going to reflect well. Are there any questions about that with midterms, other dates coming up? We'll cover it again at the end, but if you have a burning question now, we can go over it. All right. So, chapters 8, 9, and 10, we're going to kind of take our time with. We've been going through a chapter a week. These chapters are math intensive, so we're going to take our time a little bit more with these than we have been, and hopefully that will benefit you. You will need to remember the idea of unit equations and unit factors when we start doing these problems. So if that was a struggle for you, try to refresh, come to office hours, let me know. But you will need to remember that concept, and I'll help you kind of, get your memory going, and we'll do examples together. So this chapter, we're talking about the mole concept. The mole is based on Avogadro's number. Avogadro was an Italian physicist. We're not going to talk about him or his history or anything like that, but that's where it comes from. It's named for a man whose last name was Avogadro. And what his number represents is the number of atoms in 12.01 grams of carbon. That number, which is really big, is 6.02 times 10 to the 23rd. It's a lot of atoms. You will need to know this number. I am not going to put it on the equation sheet. You will need to know Avogadro's number. So make sure you commit that to memory. We'll be using it so much that by the time you get to exam time, you will know it. The reason we care about Avogadro's number is because it's connected to the mole, which is the unit of measure that we use to talk about amounts of chemical substances. Oh, sure, I can go back. So we're going to need to keep going forward so we can get through everything. If you miss a part, you can always look at the notes as a PDF on Blackboard. So the mole we care about because it's the unit of measure of how much of a chemical substance we have. A mole is 6.02 times 10 to the 23rd particles. By particles, we can say atoms or molecules. So if I had 1 mole of water, H2O, that means that I have 6.02 times 10 to the 23rd molecules of water. Does everybody understand that? That's what a mole is. I'll show you how we can use that information to convert from atoms to moles and moles to atoms. What we're doing here is we're building up our repertoire of problem types. So at the end of this, I'm going to have a cheat sheet that I'm going to fill in for you where we have the problem types that we covered today and the equivalent unit factors that you need to do those problems. So in this first problem, we're asked how many magnesium atoms are in 1.59 moles of magnesium. The first type of problem that we're going to cover is converting moles to atoms. When we're doing these types of problems, the first thing you want to do is identify the problem type, because that will show you how you need to solve the problem. Don't just go straight to your calculator, just like I was saying in chapter 2. That calculator will tell you all the sweet nothings that you want to hear. Make sure you know what you're solving for and you set up your equation first. When we're going from moles of something to atoms of something, we're always going to use Avogadro's number. We have 1.59 moles of magnesium. We want to write a unit factor using Avogadro's number Where do I put Avogadro's number? And this is kind of to help jog your memory for chapter 2. So everybody's saying bottom, but it goes in the top. Yeah. It goes in the top because we want to get rid of moles, which has to go in the bottom. Right. We're trying to get to the number of atoms, so that's going to be on the top. Now I want you to try using your calculator to get an answer for this. Keep in mind that we care about significant figures. Avogadro's number is exact, but 1.59 moles is not. There are 3 significant figures here. So try putting this into your calculator and make sure you remember how to put in scientific notation using exponents. When you get an answer, you can put it in the chat. There should be an exponent to go along with that. For some calculators, it's like in the top corner. So you should get, with sig figs, 9.57 times 10 to the 23rd magnesium atoms. Don't forget your units. Again, I am echoing chapter 2. Units are important. Don't just write numbers. Make sure that they have a unit to go along with them if they have one. Naked numbers are bad. It's getting colder outside. Put them clothes on those numbers. Give me a unit, okay? Let's do another example. Here we're asked how many moles of tin are in 1.25 times 10 to the 21 atoms of tin. And you need to express your answer in scientific notation. This is the reverse. Where is it? This is the reverse of what we did before. You're still going to use Avogadro's number, but that unit factor is going to look a little different. Where am I going to put Avogadro's number? The top or the bottom of this unit factor? Yes, it's going to go on the bottom. This time we're trying to cancel out the number of atoms. So it goes in the bottom. In the top, we're going to put 1 mole of tin. Our atoms cancel out. We're left with moles, and that's what we want. Put that into your calculator and let me know what you get. And don't forget your units. Remember, we need to do scientific notation. And we need to account for sig figs. Your calculator does not care about sig figs, and it also does not care that I asked for scientific notation. We've got 3 sig figs in the number of atoms. Avogadro's number is exact, so 3 sig figs we need to have for our answer. Make sure that you divide, not multiply. Your final answer should be 2.08 times 10 to the minus 3 moles of tin. We're brushing those cobwebs off, making sure we can still do scientific notation. So you have to divide. You're taking 1.25 times 10 to the 21 and then divide by 6.02 times 10 to the 23rd. If you're dividing by it, then you should not get an exponent that is bigger. So make sure you troubleshoot with that calculator. And we can't stay on this slide all day. But try to figure it out, help each other out in the chat. We'll do some more practice so we'll be able to make sure your calculator is all set up right. So don't get too hung up on it. So we did one problem type. Before we can introduce the next problem type, I have to introduce another concept, and that's molar mass. When you look at the periodic table, say we have sodium, that top number is the atomic number. It tells you the number of protons. That bottom number is the atomic mass. This is talking about 1 atom of sodium. But what if we had 1 mole of sodium? Now we're talking about the molar mass, which is the mass of 1 mole of a substance. The molar mass for sodium, you would take the number that's on the periodic table and express it in grams per mole. That's molar mass. The other example I have on here is carbon. So if your atomic mass for carbon is 12.01, the molar mass of carbon is 12.01 grams per mole. Does that concept make sense of molar mass? Let's add on to it. All the stuff that I'm sorry. Someone asked for me to repeat. So, atomic mass, that's what you see on the periodic table. Molar mass tells you the mass in grams of 1 mole of a substance. For any element, that's just going to be taking the atomic mass and expressing it as grams per mole. So with sodium, you look that up on the periodic table, you see 22.99. If you write grams per mole after that, that is the mass of 1 mole of sodium atoms. We're going to talk about that more here, so I'm going to do an example problem for you. And then if you still have questions about it, we can address those. I just don't want to get too far behind. By and large, we're going to encounter compounds, not just individual elements. But the concept is exactly the same. You're going to look up each of the elements that you see in the compound. Here we've got magnesium sulfate. So we've got magnesium, sulfur, and oxygen. When you look these up on the periodic table, you'll find 24.305 is the atomic mass for magnesium. We express it as grams per mole, and now we've got the molar mass. If you have your periodic table, tell me what the molar mass of sulfur is. And what about oxygen? So, for these, you typically do not round. So I wouldn't say that, oh, you can just round magnesium to 24. But oxygen is 15.999. It's okay to use 16 for that. The difference in the answer is going to be minuscule. Everything else, though, make sure that you use exactly what it says on the periodic table. Yes, there's a question. No, you don't have to. It's so the way that I grade these, I have a range. So as long as your answer fits the range, you're fine. So we're not done yet. We don't have the molar mass of magnesium sulfate. We just know the molar mass of each of the individual elements. Now we need to take into account how many of each element we have in this compound. We've only got 1 magnesium, 1 sulfur, but that subscript 4 tells us that we have 4 oxygens. So we have to multiply the molar mass of oxygen by 4 to get that. And you add all of these up. So to write it out completely, and that's the magnesium plus the sulfur plus the 4 oxygens. When you put all that into your calculator, you're going to get something in the ballpark of 120.367 grams per mole. I'm not going to be too much of a stickler for significant figures when you're doing molar mass. But mastering chemistry might be a little bit more. So just keep that in mind. Does everyone understand how we arrived at this answer? Go for it. What's your question? No, just grams per mole. Go ahead and try this second one. Calculate the molar mass of lead 2 chloride. I'll start setting it up here, but you can keep working. To figure out our molar mass, which I abbreviate molar mass, MM, we're going to need lead, which is 207.2. And then we're going to have to take what we see on the periodic table for chlorine and multiply it by 2 because we have 2 chlorine atoms. If we were using sig figs for this, the rules for adding, we would only be able to report up to that second decimal place, or up to the first decimal place, excuse me. But again, I'm not going to be a stickler for that. So are we good on calculating molar mass? For me, no. You do not need to worry about sig figs per se for molar mass. Typically speaking, that's not the end of the question. So I'm not too concerned about it. So we talked about molar mass and calculating it because we can actually use it to figure out the mass of a substance. So in this case, the question is, what is the mass of 1.33 moles of titanium? We're adding another problem type to our list. We know the number of moles, and we're trying to get to the mass in grams. To do this calculation, you're always going to need molar mass. Look up titanium on your periodic table and tell me what the molar mass is. The molar mass is 47.867 grams per mole. We can actually write this as unit factors. We've got 47.867 grams of titanium and 1 mole of titanium. And we can write the reciprocal. Does that concept make sense to everybody? We just took the molar mass and wrote it out as 2 unit factors. Now what we need to do is figure out which one of these to use. We're trying to figure out the number of grams. Yeah, you know what I want. You can write A or B or 1 or 2. We're going to use the first one. When you do that math, all you're going to do is multiply across. 1.33 times 47.867 grams. As far as units, you should have grams of titanium as part of your answer. When we're doing sig figs for this, we're only considering the information that we're given in the problem. There's 3 sig figs here, so we're going to use 3 sig figs for our answer. So you should get 63.7 grams of titanium. We good on that one? Then let's do another. Before we get there, I want to remind you that we've just done 2 problem types. We did atoms to moles, moles to atoms, and then moles to mass, and mass to moles, right? So we can actually go from the number of atoms all the way to the mass in grams using all of these different conversion factors or unit factors. So let's try it. This time, we're doing atoms to mass. But we can't go directly there. You have to recognize the problem type, which is atoms to mass. Molecules to mass would be the same idea. And then you have to know the pieces to put together to get from atoms to mass. So the first part that we can do is atoms to moles. With these problems, you're always going to have to get to moles first and then go from moles to your final destination. What number do we use to get from atoms to moles? In general, not this specific problem, in general, to go from atoms to moles, you have to use Avogadro's number. Y'all are overthinking it. Yeah, that's the 6.02 times 10 to the 23rd atoms. The second part, we have to take those moles and get to mass. Now we just did that. What do we have to use to get from moles to mass? The hint is there's mass in the name of it. Molar mass, which I abbreviate MM. So the molar mass of carbon, you just look at the periodic table. That's 12.01 grams per mole. Now we've got all the information we need to set up the problem. I'll write each part of the equation in a different color so you can kind of track it. So the first part, we're taking the number of atoms we have, which is in the problem, 4.55 times 10 to the 23rd carbon atoms. We need a unit factor to get us from atoms to moles. So where am I going to put Avogadro's number? The top or the bottom? We're going to put it in the bottom. What goes in the top? Always make sure you know your units. So we're talking about 1 mole of carbon. That goes in the top. Not just one mole. For the second part, we need to write a unit factor that's going to take us from the number of moles of carbon to the number of grams of carbon. That means I'm going to put my grams in the top and moles in the bottom. You can cancel out your units. And remember, to cancel, you have to have something in the top and the bottom. So we're left with grams of carbon. Does everybody follow so far how we set this up? Because if you can set it up, that's most of the points. Okay. Try putting it in your calculator and see what you get. Anybody else? So I got 9.08 grams too. Now in that case, if you're off by a little bit, you might lose like half a point. If you set it up right, and maybe you just wrote it wrong or something weird happened, you're not going to lose a ton of credit. The main part is setting up this equation. So how do we feel about that? Let's try another one. Same type of question, but we've got a different molecule. I want you to try this one. I'll give you 3 minutes and try to work out this problem. It's the same exact thing we just did, only instead of carbon, it's carbon dioxide. Give it a shot. I'm going to start setting up the problem here. I'm going to write it out using the same color scheme as before. So when you're looking back at it, if you need to, you can match it up. So in the first part, you're converting those molecules to moles. The second part, you're converting the moles to grams. And with sig figs, you should get 33.3 grams of carbon dioxide. Questions on that? All right. Let's go in the opposite direction. I'm going to let you try this one first, and then I'll work it out. I'll give you 3 minutes to get started. I'm going to start setting up the problem, but you can still keep working. When you get an answer, you can put it in the chat. You can also let me know if you're stuck. That's helpful information too. So this problem is literally what we did in reverse. You're starting with a mass, which is 2.25 grams of oxygen gas. And you have to figure out how many molecules you have. Starting with the mass, the only way that you can get to moles is using molar mass. For oxygen gas, there are 2 oxygen atoms, so 2 times 16 is 32. The next part, we're going to take the moles and convert that to molecules. We have to use Avogadro's number for that. I'm going to make you hold tight on that answer, Whitney, so just bear with me. So you can match it up like last time. I'm going to do purple for the mass to moles. We're starting with 2.25 grams of oxygen. And we need to use our molar mass to get from grams to moles. Where am I going to put my grams? Top or the bottom? We're going to put them on the bottom, that's right. Because we have to be able to cancel them out. On the top, you're going to put 1 mole of oxygen gas. If you did that and stopped there, you'd know how many moles of oxygen gas you have in 2.25 grams. But the question is asking us about molecules. For that, we have to go to Avogadro's number. If I'm trying to get to molecules, am I putting Avogadro's number in the top or the bottom? Putting it in the top. In the bottom, we're going to put 1 mole of oxygen. At the end of the day, we're left with molecules, which is what we want. With sig figs, you should get 4.23 times 10 to the 23rd oxygen molecules. So for those of you who got stuck, did this help? Does it make a little bit more sense now? And notice how we have the same kind of modules, mass to moles and moles to molecules. We're just switching the order. So if you can do the simpler problem types, you can string those together to do the more complex ones. Oh, whoops, I wrote 23rd. It should be 22nd. It should be 22nd. So don't get scared. That was just me writing fast. So we've got one more problem to do, and then we'll take a very short break. We're going to figure out the mass of a single molecule of sodium chloride. Sounds like it's a hard problem, like something that we haven't done, but we have. This is a molecule to mass problem. We've already done something like this. For the first part, you have to convert the number of molecules you have to the number of moles using Avogadro's number. And for the second part, you take those moles and convert it to mass using the molar mass of sodium chloride. Now, I'm telling you this specifically because you're going to have a question like this on your exam. I put one on there every semester. So you need to know how to do this type of problem. We need to figure out our molar mass. So you take the numbers from the periodic table for sodium and chlorine and add them together. Now we need to write our equation. We're trying to find the mass of a single molecule. So that's what we're starting with. Then we're going to use Avogadro's number to convert that to moles. The last piece is using the molar mass to go from moles to grams. When you go through and cancel, you should be left with grams of sodium chloride. And you should get a really small answer. And in this case, I would tell you how many significant figures to report. So don't get frightened when you see what is the mass of a single molecule or a single atom of something. It's a molecule to mass problem. You just have one molecule or one atom instead of a bunch of them. So is that clear? This is a good time to take a break because we're going to switch gears a little bit and talk about one more problem type, but we need to introduce a couple more concepts before we get there. So we'll take a 5-minute break, 5-minute-ish. We'll break till 3:23 p.m. We've got some more to cover, so it can only be a 5-minute break. I apologize. But I'll see you back soon. 5 minutes. All right, everybody. It's 3:23. We're going to keep pushing ahead. Like I said right before break, we're going to switch gears a little bit. We're still talking about moles, but we're going to talk about a special case for gases. So this next topic is molar volume. There's a set of conditions called standard temperature and pressure, where the temperature is 0 degrees Celsius and the pressure is 1 atmosphere. Standard temperature and pressure you'll also see abbreviated as STP. 1 mole of any gas at STP has a volume of 22.4 liters. Again, this is only for gases at STP. That volume, the 22.4 liters, that's the molar volume. So for gases only, we can say that 1 mole of gas has 6.02 times 10 to the 23rd gas molecules, and that it has a volume of 22.4 liters. That's molar volume. But how do we use molar volume? Let's say we have a sample of propane. That's a gas. It's usually used for cooking and stuff like that. If you have a gas grill, it's going to be propane. And it occupies, sure, give me 1 second. There you go. You're welcome. So how do we use molar volume? We've got a sample of propane and it occupies 4.50 liters at STP. How many moles of propane are present? Couple of things. Anytime you see a volume, whether it's in liters or milliliters, or you see STP, that instantly should bring to mind that you're talking about a gas. And our question is asking how many moles, and we have a volume. So this problem type, which is specific for gas, is volume to moles. You could also do the reverse. For this problem type, you're always going to use molar volume, which I abbreviate MV. One mole of gas is equal to 22.4 liters. The way we set this problem up is we take our volume and we use the molar volume to write a unit factor to convert. Now we've got liters here, and we're saying 1 mole of gas is equal to 22.4 liters. If that's my unit equation, what's my unit factor going to be? What am I going to put in these parentheses? We're going to put the 1 mole of gas on top, In this case, we're talking about propane. And the volume on the bottom. Because we're trying to get rid of those liters. So now we should be left with moles. When you divide, you should get 0.201 moles of propane. So that's molar volume. We can go from volume to moles and moles to volume. I want you to try it. Oh, sure, I can go over it again. I'll go over it again, and then I want you to try a problem exactly like it. So we're starting with the question of how many moles of propane are present, and we're given a volume. Anytime you're given a volume and you're told that something is at STP, you know you're dealing with a gas. And only gases deal with molar volume. So this problem type is volume to moles. We're going to use molar volume where we know 1 mole of gas is equal to 22.4 liters. And we're going to write a unit factor from that unit equation to convert from the liters that we have to the moles that we want. We take those 4.50 liters. The 22.4 is an exact number. That is just a statement. So if I go back one more, we covered that here. The volume occupied by 1 mole of gas is 22.4 liters. Okay. So that's something else that you will have to know. You write your unit factor, making sure that you can cancel out those liters, and then you do the math. Now I want you guys to try a problem. I'll give you 2 minutes to get started. I'll start writing out how to solve the problem. You can keep working and put your answer in the chat. We're starting with 6.85 liters of oxygen gas. And we need to get to moles. Same thing as before. Volume to mass question. So we're going to use molar volume. We know that 1 mole of any gas at STP has a volume of 22.4 liters. We're going to put that 22.4 liters down at the bottom so that it cancels out, and 1 mole at the top. You should be left with the units of moles of oxygen gas. And when you do the math, 0.306 moles of oxygen gas. So how does that feel now? We're going to add on one more concept that is specific for gases. So I'm glad everybody's doing good. We're going to bring up density again. We talked about density in chapter 2, But we were really talking about solids and liquids. We didn't acknowledge gases. Now we're going to. The density of gases is much, much less than that of liquids or solids. If you remember from chapter 3, when we were talking about the states of matter, gas particles are really, really far apart. So the amount of gas that can fit in a volume is pretty low. They spread out really far. So density for a gas at STP can be defined as the molar mass in grams divided by the molar volume in liters. So if I had 1 mole of oxygen gas at STP, I could calculate its density because I can calculate the molar mass. The molar mass of oxygen we get 32 grams per mole there. And if we have 1 mole of it, the volume is equal to 22.4 liters. So our molar mass expressed in grams divided by the molar volume would give us the density. Does that concept make sense? Now remember from chapter, sure, I'll go over it again when I talk about density a little bit more. The other way that we can define density is simply mass divided by volume. So if you know the mass of the gas and the volume that it takes up, you can calculate the density. This is just a second way to do it. And to repeat the second way, you have to have the molar mass of your gas, which you can figure out from the periodic table. And then you know the molar volume in liters. 1 mole of any gas has a volume of 22.4 liters. You can use 22.4 liters as the volume if you're using the molar mass in the top. So that's the caveat here. If you're dividing the molar mass by the molar volume, you will get the density. Anything outside of that, it's a case-by-case basis. And we're going to solve some problems so you can see the difference. Is that fair? So I always think it's better to use examples and solve some problems anyway to show, a concept. So let's do that. And then if you still have some questions, that we can go over those. So here's the first one. What is the density of propane gas at STP? We're looking for density at STP. Since we see STP, that means that we can use molar mass over molar volume. Take a second and figure out what the molar mass of propane gas is. When you figure it out, you can put it in the chat. So you should get something in the ballpark of 44. So if it's 44.097 versus 44.094, that's not a big deal. You'll still get the same answer at the end. Now that we've got our molar mass, we can calculate the density. Now note here we are using the molar volume. And that's because we're assuming that we have 1 mole of gas. If we have anything else, anything other than 1 mole of gas, we can't use molar volume. And I'll show you an example of that in a minute. If you put this in your calculator and you take into account sig figs, which we're just going to do 3 sig figs for now, you should get 1.97 grams per liter. And note that's grams per liter, not milliliter, not centimeter cubed. Does this one make sense to you? Just an example of using the molar mass divided by molar volume. We're going to do another problem that's a little bit more complicated. So let's move on to that slightly more complicated problem. Let's say that we have an unknown gas. We know its mass, and we know the volume that it occupies at STP. But what we don't know is the molar mass of the gas. That's what we're going to calculate. This is still a density problem because we have a mass and a volume. We can always calculate density if we have mass and volume. If we're at STP, which it says we are, then that density that we calculate is also going to be equal to the molar mass divided by the molar volume. So step 1 is going to be calculating the density. Step 2, we're going to use the density to solve for molar mass. So I'll let that simmer for a second. Let me know if that makes sense to you, that plan. If you have questions, this is a good time to ask them. All right, since I don't see any questions, I'm going to go ahead and put some numbers to this. For the first part, we're calculating the density. That's simply taking what we're given in the problem. We've got 2.36 grams of our gas. And the volume is 1.50 liters. Do the division. And that's our density. I'm not doing any sig figs yet because that's not our final answer. And we want to carry over as many digits as we can until the end. So this is the density of the unknown gas. Now we're going to use that density to solve for the molar mass. This time, we can put in 22.4 as our volume because we're solving for the molar mass. And molar mass over molar volume gives us the density as well. You multiply by 22.4 liters on both sides. And you should get 35.2 grams per mole as your molar mass. Let that simmer for a second. Let me know if you follow. You will see a question like this on your exam. I can go over it again. We're starting with an unknown gas. We know what its mass and we know its volume in STP. We're asked to calculate the molar mass. For this, we're going to have to use two definitions of density. The first one is the one that we encountered in Chapter 2. Density is equal to mass times volume. We have a mass, we have a volume, so we can calculate density. So that's what we did here. 2.36 divided by 1.5, you get 1.733333. That's our density of the unknown gas. But that's not the question. The question is, what's the molar mass of the gas? We have another definition of density that we can use specifically for gases. The molar mass of the gas divided by the molar volume. And we're assuming that we have 1 mole of gas here. 1 mole of gas will always take up 22.4 liters. So that is our molar volume. We calculated our density using the given information, which means that we can solve for that molar mass. You multiply by 22.4 on both sides, and you should get 35.2 grams per mole. How do we feel about that one? You will have a question like this on the exam, so make sure that you can do a problem like this. Go for it. If we were, yeah. Yeah, if you were just asked what the density is, then you'd stop at the first part. Does that answer your question? Great. Other questions, or are we ready to move on? Then let's go. Now we've got 3 different ways that we can talk about a mole. We've got 1 mole is equal to 6.02 times 10 to the 23rd particles. And that's using Avogadro's number. We've got 1 mole is equal to the molar mass of a substance in grams. And then this third one, 1 mole for gases, takes up a volume of 22.4 liters at STP. Now that at STP part is important because when we get to chapter 10, we may not be at standard temperature and pressure. So for now, you're only going to see at STP. But in chapter 10, when we revisit this, things can get a little bit more complicated. Since we have 3 different ways to talk about a mole, that means that we can kind of use all of these interpretations to do even more complex math. Hooray. So let's do some more work with gases. Another problem type that's going to be added to our cheat sheet at the end, we're going to go from a volume of a gas to the number of molecules or atoms. It's the same thing. So this is another problem type that we're solving. We took a little detour to talk about gas density, but now we're back to talking about problem solving skills. For the first part of this, we have to figure out how to go from a volume to moles. Because remember, we're always trying to get to moles as that intermediary. We can't do anything else outside of that. What do we use to go from a volume to moles if we're talking about a gas at STP? We're going to use that 22.4 liters, which is called the molar volume. The second part is something that we've been doing. We need to take those moles and convert to molecules. What do we use to do that? Yeah, it's that 6.02 number, which is called Avogadro's number. I'll write in different colors just like I did before. The first part of our equation is going to be setting up the volume to moles. Our starting volume is 0.430 liters of xenon gas. We're trying to get 2 moles. So where am I going to put that 22.4 liters, the top or the bottom? We're going to put it on the bottom, because we're trying to get rid of those liters. Don't forget that on top, we have 1 mole of xenon gas. To go from moles to molecules, we need a unit factor that has Avogadro's number. Where's his number going? The top or the bottom? It's going on top. On the bottom, we put 1 mole of xenon gas. So don't forget about those units when you're writing in the rest of your bridges. We can cancel out those liters. We cancel out the moles, and we're left with molecules. Put that into your calculator and let me know what you get. Your calculator is going to give you something like that. We are rounding. Your calculator is going to give you something like that. You need 3 sig figs. So that's going from volume to molecules or atoms. Again, notice all we did was break it down into 2 simpler types that we've already solved. So how did that one feel? I'm glad you sorted it out. And for the rounding, we need 3 decimal places. So that 5 is the one that we're going to round. So make sure that you round appropriately. Just review that, because we haven't been doing this for a while. So bringing up sig figs, scientific notation, and conversions, bringing all of that back out of nowhere could be a little bit harsh. Yeah, you got to make sure that you do that division. Otherwise, you will get a very different number. But again, if you write this part out, and then when you put it in your calculator, you just forget to do the division, you'll get most of the points for that problem. Because anybody can just put numbers into a calculator until they get a number. But if you show me how you set it up, then I know that you understand the question. And that's more important to me than the final answer. Let's do one more. This time you've got a mass, or you're looking for a mass, and you're starting with the volume. So I'll help you out a little bit to help show you which 2 problem types we're solving here, and then I want you to take a shot at it. We've got a volume of nitrogen gas. You need to convert that to moles first. Once you have the number of moles, you can convert that to mass. So I'm not going to tell you what you need to use for these two. I want you to figure that out. I'll give you 3 minutes to get started, and then I'll start filling things in. You can keep working. I'm going to start solving things and writing out equations. So if you're stuck, I might be able to help you out. But you can put your answer in the chat. For the first part, volume to moles, we're going to use molar volume. In the second part, to go from moles to mass, you're going to use the molar mass of nitrogen gas. Now let's put it all together. For our first unit factor, we're using molar volume. The liters are going to go in the bottom so that they cancel, and the 1 mole will go in the top. Yeah, that's fine if you use 14.007. You'll get the same answer. So at the end of it, you should get 4.2 grams of nitrogen gas. And you should have 3 sig figs here. How did we do on that one? I know a few of y'all got it. Go for it. What's your question? So order of operations shouldn't really matter here because it's all multiplication and division. But depending on how you put it in, it could matter. And without seeing exactly what you did, I can't diagnose it. But this is what I did when I put it into my calculator. And you can break it up if you want to. So I put that whole string in and got that answer. You should be able to do that. Yeah. So something small like that, and you get an answer that's pretty close. You'll either get credit, full credit, or at most you'll lose a half point. Okay. You're welcome. Make sure that you show your work. On this upcoming exam, you need to show your work, particularly for these problems. If you don't show your work, then you can't get any partial credit. And when I grade chapter check-ins, I need to see this work as part of your answer. Even if you got the right answer, you're not going to get full credit because I need to see where you got it from. Are there any other questions on this? Then let's fill in that cheat sheet I was talking to you about. We've got all these different problem types that we've solved. I'm going to label these a little bit. So the first one, we've got moles to atoms or molecules. We're going to pair that up with atoms or molecules to moles because we're using the same concept here. Avogadro's number. But the unit factor is different. If we're trying to go from moles to atoms, then we're going to put moles at the bottom and Avogadro's number at the top. If we're going from atoms or molecules to moles, we're going to flip that over. So I'm just writing atoms, but it's the same thing for molecules. The next thing we talked about was molar mass and how we can use that to go from moles to mass and mass to moles. Same concept, different unit factors. If you're trying to figure out the mass, you're going to put your grams of substance on top and the 1 mole on the bottom. But if you've already got a mass and you need to figure out how many moles you have, you need the reciprocal. That's 1 mole on top and your grams of substance on the bottom. The third problem type that we covered that is specific to gases was molar volume. If we need to go from the number of moles to volume of gas, you're going to have moles in the bottom and the molar volume, 22.4 liters, on the top. If you're starting with the volume and you need to figure out how many moles you have, you need the reciprocal. So there's the concept and the unit factor that you need for each of the problem types that we covered. Density is not covered on this cheat sheet because it doesn't really fit. But you'll need to remember that too. But that's kind of its own thing. This will be really helpful for the mole calculations you need to do for your homework. You can't use this on the exam, but if as you practice, it will become, it'll kind of become ingrained in you what you need to do. So if you didn't get a chance to write this down, you can print it out or you can go back to the notes later. Are there any questions about this? Because this is gold right here. No. But for the final exam, I let you have one note card front and back. So this would be something great to put on there for that. But for the upcoming exam, no. Any other questions? All right. So as usual, I've got reminders for you all. Midterm grades submitted this week. I'm going to try to submit them on Thursday, which means that your grades are going to be updated Wednesday, Thursday. So you can check Blackboard and see where you're at. I think I said this in the beginning, but it's going to include everything that we've done up through the exam that you took over the weekend. That includes the Chapter 7 Mastering Chemistry assignments as well. You've got a Chapter 8 check-in that's going to be due on Sunday. There's going to be a video posted either tomorrow or Thursday. But it's just going to be one or two two problems, not one or two. It's two problems that you need to do. And it's just like the ones we've been doing. So you'll need to submit that on Sunday at the latest. And this is a little bit of a departure from the syllabus because I'm breaking up the chapter check-in and the Mastering Chemistry. Your Mastering Chemistry for Chapter 8 isn't due until October 25th. So that week you will not have a chapter check-in, but you will have to finish that Mastering Chemistry homework. And I know someone asked about Exam 4 and my brain just didn't have the dates in there, but I knew I had it somewhere. Your last regular exam is going to cover Chapters 7 and 8. And that's going to be at the end of this month. Wednesday, October 28th, it will become available. Yeah, so there's still a final exam. And we still have more material to cover, but you're not going to have an Exam 5. So after we cover Chapters 7 and 8, then we're going to have 9 and 10. And your final exam is pretty much going to be an exam on Chapters 9 and 10, plus an exam on chapters, all the previous chapters. So that will definitely be a 2-hour exam.